Welcome to week 2 of pre-calculus. Our first topic this week is linear functions. Well, let's start with the formal definition. By a linear function, we will mean a function of the form mx plus b, where m and b are constants. Linear functions represent quantities that change by a constant value every unit of time. And this is in sharp contrast with quantities that change by a constant factor per unit of time. These are exponential functions, and they will be introduced later in this course. So this first comment is very important. One should not confuse linear functions with exponential functions. Again, the difference is that linear function change by a constant quantity every unit of time. And that is really easy to see why, because if we have our function in the form mx plus b, and x is time, so your quantity at time x is mx plus b. Let's compute the quantity at the time x plus 1. It will naturally be m. Instead of x, you write x plus 1 plus b, which is mx plus m plus b. And if you subtract the quantity at time x plus 1 minus the quantity at time x, right? In other words, you subtract, you compute this minus this, this minus this. So what's left is m. Every unit of time, every hour, for instance, if x is measured in hours, every hour your quantity grows or decays by m, depending on whether m is positive or negative. In exponential functions, the change is by a constant factor. A constant factor per unit of time. So, for example, if a bacteria colony doubles in size every hour, it starts with 1 unit of amount. In 1 hour, it will be 2. In another hour, it will be 4. In another hour, it will be 8, and so on. Note that the difference between two time steps is changing. We started with 1 and grew by 1. Then we start with 2 and go to 4, and we grow by 3. Then we grow by 4. Then we grow by 8, and so on. Right? This is not the growth with constant additive value per unit of time. This is growth with constant factor per unit of time. This is exponential growth. So please do not confuse linear functions and exponential functions. And again, exponential functions will be introduced later in this course. But let us look at an example. So in this example, we have a train whose distance is measured from the train station as a function of time. It's known that the train moves at a constant speed. And also, it's known that every unit of time, every second, the distance from the train to the station increases by 83 meters. We're also told that we start our observation at the time when the train was 250 meters from the train station. So this is an example of a linear function, because if we write the distance from the train to the train stations to the train station at different times, at 0 seconds, at 1 second, at 2 seconds, at 3 seconds, we can easily see that we are actually told that the distance between the train and the train station grows by 83 meters every unit of time. Again, as an example of growth with constant factor per unit of time, think of that example with bacteria colony. A bacteria colony may double in size every hour. That would be an example of exponential growth. All right, some basic facts about linear functions. Well, first and foremost, the graph of a linear function is a straight line. In the context of linear functions, the number m is called the slope, and the number b is called the y-intercept. Well, the terminology is easy to explain, and we will do this on the next page. But right now we can look at how number m, the slope, governs whether our linear function is increasing or decreasing, or actually is a constant function. We have the following theorem. For a linear function mx plus b, whenever m is positive, we have f increasing. Whenever m is negative, we have m decreasing. Excuse me, this is actually a mistake. F is decreasing when m is negative. And whenever m is 0, we simply have the constant function f equals b. I hope everyone remembers what these terms are: increasing, decreasing. We can remind ourselves. So in this picture, m is greater than 0, m is positive, and this function is increasing. So what does that mean? It means that if you take two values of x, x1 and x2, where x1 is less than x2, whatever value is greater, x2 in my case, will be matched with the greater value of y. So increasing means that x2 being greater than x1 implies that f at x2, which is y2, is greater than f at x1, which is y1. For the decreasing function, the situation is opposite. In this picture, m is negative. And if we now consider two values of the x variable, x1 again is less than x2, the corresponding values of y are in the opposite relation. Now, x2 being greater than x1 implies that f at x2 is less than f at x1. And we can see that in the picture. The value y2 corresponding to the value x2 is less than the value y1, which corresponds to x1. Finally, for the constant function, which corresponds to the situation m equals 0, the value of f is the same for all x's. That's what it means to be a constant function. All right. Now, I'd like to say a few words about slope. We already saw that slope has this meaning that slope is that value by which our function grows or decays every unit of time, provided, of course, our function is linear. But now a little bit more about slope. Suppose we have two values of the independent variable, x1 and x2, and suppose that the corresponding values of the dependent variable are y1 and y2. In other words, f at x1 is y1, and f at x2 is y2. What we claim is that slope is the ratio of the change in the function delta y, change in the output, sometimes called rise, over change in the independent variable, sometimes called run. So it's very easy to memorize that slope is rise over run. And because change in the variable is new value minus old value, in other words, y2 minus y1, if we think of x1, y1 as the old point and x2, y2 as the new point. So we subtract new y value minus old y value, that'd be the rise, and likewise the run is the new x value, x2, minus the old x value, x1. This is easy to visualize. So this is our point x1, y1. This is point x2, y2. This here distance in red is run, and the distance in green is rise. Slope is precisely rise over run, or delta y over delta x, and it's easy to explain why. Let's consider a particular situation when change in the independent variable run is 1. In other words, what happens if delta x, which is x2 minus x1, is 1, i.e. x2 equals x1 plus 1? Well, then y2 being f at x2 being f at x1 plus y1, which is m at x1 plus y1 plus b. That is what y2 is. So let us now compute delta y over delta x. Well, delta y is y2 minus y1, and delta x is x2 minus x1, which we agreed is 1. So this simply is y2 minus y1. Now, y2, as we just computed, is mx1 plus 1 plus b, and y1 is f at x1, which is mx1 plus b. When you do the algebra, m times x1 and negative m times x1 cancel out, so do b and negative b, and what is left is simply m. And the characteristic feature of linear function is that slope, the ratio of the change in the dependent variable by the change in the independent variable, remains constant at all pairs of points in a nonlinear function. In a nonlinear function, this ratio delta y over delta x generally is not constant, right? If you take point x1 y1, x2 y2, and x3 y3 in a nonlinear example, delta y over delta x for these 2 points will not be the same as delta y over delta x for these 2 points. Delta y over delta x is much greater for this pair of points than it is for that pair of points. But for the linear function, delta y over delta x, change in y over change in x, remains constant no matter what pair of points you look at. All right, hopefully that makes sense. Another important point to make here is that units of slope, because slope is change in the y, which is rise, divided by change in x, which is run, are units of y over units of x. So for example, if we go to the previous page and look at the example 0.1, the train example, this number 83 has a clear physical meaning, which is easy to understand if you think about what units that number 83 has. In what units is it measured? Well, units of d, units of the function in this example, are meters. And units of t, time, in this example are seconds. So naturally, the slope 83 is measured in meters per second. And of course, you immediately recognize that this is simply the speed at which the train is departing from the station. the train is moving away from the station at the constant speed of 83 meters per second. And again, it's important to remember that slope has units which are ratio of the units of y over units of x. All right, let us solve a simple example. So we know f is a linear function, and we also know that points 3, -2 and 8, 1 are points on the line, which is the graph of f. And the question is asking us if this function is increasing or decreasing, and it's asking us to find the slope. So how do we find the slope? Well, we find the slope by the very formula that we just discussed, rise over run, or delta y over delta x, or if you wish, y1 minus y2 minus y1 over x2 minus x1. Where, of course, it doesn't matter which point you declare the first, which point you declare the second. You get the same result either way. Let's say point 3, -2 is 0.1 and 0.8, 1 is 0.2. And so in this computation, we have y2 being 1 minus y1, which is -2, and the difference of x's. We declared 8 to be the second x, and then 3 is the first x. And so we have 3 over 5 as slope, and by the theorem on the previous page, because the slope is positive, we have our function increasing. F of x is increasing. All right. So far, we have only talked about this form of equation of straight lines, mx plus b, called the slope-intercept form. The reason why mx plus b is called slope-intercept form is because m is slope, and as you can easily see, b is the y-intercept. Well, this is because, let me go to the previous page. Of course, if you consider the value of a linear function at 0, that'll be m times 0 plus b, which is b, and whatever the graph of your linear function look like, it will pass through the point 0b, and so it makes perfect sense that b is called y-intercept. And now it makes perfect sense why mx plus b is called slope-intercept form. There are, however, various other forms to write straight lines. One of them is the point-slope form. Let us discuss what that is. Suppose we are looking to write down the equation of a straight line about which we know that its slope is m, and that the line passes through the point with known coordinates x1 and y1. Well, first of all, realize that this information should be enough to find the desired line, because if you visualize this on the plane, here is your point x1, y1. There are, of course, infinitely many lines passing through the point x1, y1, but only one of them, only one of these infinitely many lines will have the desired slope m. And the question that we are trying to answer in this context is, how do we find the equation of that line? Suppose, again, that line is this one. Of all infinitely many lines passing through the point x1, y1, we want the one whose slope is m, the prescribed number that we have. So the idea behind deriving the desired equation is this. Let x comma y be a generic point in the plane. You can imagine this point flying around in the plane as it pleases. Occasionally that point will be on the line. Sometimes this point will be off the line. And we want a necessary and sufficient condition that ensures that the point with coordinates x, y is on the line. When will the point with coordinates x comma y be on the line? You can easily understand, it's clear from the picture, that the point with coordinates x comma y will be on the line if and only if, that's a necessary and sufficient condition, rise over run, which is y minus y1 over x minus x1, is precisely the prescribed number m, is precisely the prescribed slope. That is the condition that is necessary and sufficient for the point x comma y to be on the line whose equation we're looking for. Again, it means that m is y minus y1 over x minus x1. And if you clear the denominator, you have that y minus y1 equals m times x minus x1. That form of equation is called the point-slope form. Again, it makes perfect sense because this form allows you to write down the equation of a straight line in the situation when you know a single point through which your line passes and you know the slope of that line. Let us now look at some examples. In example 3, we need to write the point-slope form of an equation of a line with a slope of 3 that passes through the point 6 comma negative 1. Then we need to rewrite it in the slope-intercept form. Remember, slope-intercept form is the mx plus b form. Well, we can easily do that. In the point-slope form, we have y minus y1. y1 in our situation is negative 1 equals m, the slope, which is 3, times x minus the x-coordinate of the point through which the line passes, which in our situation is 6. So that is the point-slope form. And if we want the slope-intercept form, then we can easily compute that y equals 3x minus 19. That will be the slope-intercept form. Now, in example 4, we need to write the point-slope form of an equation of a line that passes through two given points. The points are -1 and 3 and 0, 0. So we start by finding the slope of that line. Again, it doesn't matter which of these 2 points you call the first point, which of these 2 points you call the second point. Slope is delta y delta x. Let me count these points in the same order as they appear in the problem. Say -1, 3 will be the first point, and 0, 0 will be the second point. And then slope is rise, which is 0 minus 3, over run, which is 0 minus -1. And that is, of course, -3. Now, using the point-slope form, we write that y minus the y-coordinate of a point on the line, you can use either of the 2 points, -1, 3 or 0, 0. That is not important. I will go with 0, 0 simply because it's less work. Y minus the y-coordinate equals slope, which is -3, times x minus the x-coordinate of the point. In other words, y equals -3x, the point-slope form of that line. Note, by the way, that this line passes through the origin, and indeed, that is actually given. It passes through 0, 0. The b term is missing, right? There's no b, which means that the line passes through the origin with slope -3. That finishes the example. All right, maybe a couple more examples. In this first example, we need to recognize the line from a picture. We're given the picture of a line, and we need to write down its equation. And in the second example, example 6, we're given the table representing a supposedly linear function whose analytic formula we need to write down. So for the first example, let me zoom in. Let us start by finding the slope. The slope is, as always, rise over run, delta y over delta x. And you can pick any 2 points for which computing rise and run is simple. I can pick points 0, 2, and say point 2, 8. So for these 2 points, rise is 8 minus 2, or 6. We have grown up by 6 units when we move from point 0, 2 to point 2, 8. And run is 2 minus 0. So the slope is 6 divided by 2, 3. Now we can, for instance, use the slope intercept form. And say that y equals slope 3 times x plus the y-intercept, and clearly y-intercept is 2. Or we could as well use the point slope form. And write that y minus the y-coordinate of a point, doesn't matter which point, we can use that point just for variety. 8 equals slope 3 times x minus the x-coordinate of the point, which is 2. And you can check that these are indeed the same equation. If you do the algebra, it's y minus 8 equals 3x minus 6. And moving negative 8 to the other side, we get y equals 3x plus 2, which is exactly what we had before. Now, in example 6, we have a table which relates the number of rats in a population to time. And it is given to us that this is a linear function. Note, by the way, that simply by looking at the table, we couldn't for sure say that this was a linear function. We could make that assumption, or we could make this hypothesis that this might be a linear function. But looking just at a few values could not tell you that this was indeed a linear function. We're given ahead of time that this is a linear function. Now, we naturally look for this function in the form P of W equals MW plus B, where M and B are to be found. We can easily find slope M, again as delta function, which is P, delta P over delta W, rise over run. You can again, as always, pick any 2 points. I will pick the first 2. It doesn't really matter when computing my deltas. So the new value for P is 1080, and the old value is 1000. And time grew from 0 to 2. So that is 40. Now I can write my function as MW plus B, and clearly B, being the y-intercept, is simply the value of P at 0, which is 1000. So I can write P of W as 40W plus 1000. All right, this is it for basic facts about linear functions. Next, we will talk about graphs of linear functions. That'll be topic 2. Thank you.